Perfect. So I see that Alex has turned on the recording. I want to say a warm welcome to everyone to the Graduate Online Combinatorics Colloquium. Today, I'm ecstatic to announce that we have Sylvester Zhang, who's a student at the University of Minnesota. And before he gives his talk, I want to talk about our community statement, and I forgot to pull it up, so give me a second. So Sylvester's going to talk about Schur and LLT polynomials from lattice models. While he's giving his talk, I want to remind you of the 3 guiding principles of the Graduate Online Combinatorics Colloquium. So these are sort of explained in depth in our community statement, but I just want to remind you of the 3 catchphrases. 1, we are all learning. 2, everyone has something to contribute. And 3, no one knows all the answers. With that in mind, I want to encourage you guys to ask questions, either by unmuting yourself and asking, or by typing them into the chat. And Alex, Andres, and I will try and keep an eye on the chat. And if Sylvester misses one of the messages coming in, or if there's a lot of chatter, we'll unmute and ask on your behalf. And if Sylvester doesn't know the answer, because we don't all have the answers, then maybe someone else in the audience will also have thoughts or suggestions. Okay, without any further ado, take it away.
All right, thanks, Galen, for the introduction, and thanks for the organizers for inviting me, and also thanks everyone for coming. So I'm going to be talking about Schur polynomials and LLT polynomials from lattice models. So this was an REU work with Michael Curran, Kelvin Yoswov, and Valerie Zhang, and we under the mentorship of Ben Burbiker, Claire Fischette, and Katie Weber. So, I'm going to start with the outline of my talk. So I'm going to start by introducing some basic notations and definitions of symmetric functions, semi-standard Young tableaux, and Schur polynomials. And then I'm going to start to talk about ICE models in statistical physics and how we can use it to study Schur polynomials. And then I'm going to define Riemann tableaux and LLT polynomials, which are generating functions of these tableaux. And so the main result of this talk is going to be a lattice model for LLT polynomials. And so I just want to put a note here that there is a same, like up to a bijection, the same model was also proposed by Cortillo, Keating, and Mesa in this recent archive preprint. And there's also a very recent, like amazing work of Agarwal, Borodin, and Wheeler, which is what they call the colored fermionic vertex model, which is like a very general lattice model, which is specialized to McDonald, non-symmetric McDonald, LLT, factorial LLT, and lattice models. I mean polynomials. So this is like the king of lattice models. And at the end, I'll talk about Yang-Baxter equation and how it implies that the polynomials are in fact symmetric, and some ways that we can use it to study the symmetric polynomials. All right. So we're going to say lambda, which is a sequence of integers, lambda 1, lambda 2, up to lambda k, is a partition if it's weakly increasing and is sum up to a number n. So we're going to say lambda is a partition of n. Oops. Okay, so the integer partitions can be represented by Young diagrams, which are an array of boxes. So for example, here we have a partition 5, 3, 3, 1. So in the first row, we have 5 boxes. In the second row, we have 3 boxes, and so on. And so a Young tableau is a filling of a Young diagram with integers. And it's going to be called semi-standard if the row entries are weakly increasing and the column entries are strictly increasing. And we denote SSYT sub lambda over n to be the set of all semi-standard Young tableaux with whose shape is lambda. And by shape, I mean the Young diagram is the partition lambda. And here n, I forgot to write, but it means the maximal entry of integers that you can put in this tableau is n. Okay, so here are 2 examples of semi-standard Young tableau. As you can see, the first one, we have the maximal entry is 3, and the rows are weakly increasing, the columns are strictly increasing. And for the second one, the maximal entry is 3 and the partition is 4, 4, 3, 1. Okay, so we're going to define a weight on these semi-standard Young tablocks. It's going to be basically the weight of the tablock is the product of xi to the number of the integer I in the tablocks. So for example, here in this tableau, there is one in it. So we got x1 to the power of 1. And there are 3 2's in it. So we get x2 to the power of 3. And there are 4 of 3's and 4 of 4's. Okay. And now with this weight, we can define a polynomial indexed by a partition, which is called the Schur polynomial, which is just you sum up all the weights of all semi-standard Young tablocks of this partition lambda. And so here is an example. We take the partition 3, 1, and we let the maximal entry to be 2. So it's going to be a polynomial on 2 variables. And there are 3 possible semi-standard Young tableau of this shape. And the polynomial is given right here. So Schur polynomials are symmetric, which means that if you put a permutation on the indices of the variables, the polynomial is invariant. So it's invariant under the symmetric group action, which means that if you permute the variables, it doesn't change the polynomial. So in this example here, like if you change x1 and x2, the first term will become x2 cubed x1, but the third term will become x1 cubed times x2. So it's indeed symmetric. All right, so before I start to talk about different objects, are there any questions? All right, so now I'm gonna switch gears and talk about some physics. So a 2-dimensional ice model is like you have a bunch of hydrogen and oxygen atoms in this way, and then we want to connect these atoms so that we're going to create a bunch of H2Os. For example, here is one possible state of this model. As you can see, one oxygen is always going to be connected to 2 hydrogen atoms. And here is another state of this model. And so we're gonna like study these ice models in a different way by putting them on a square lattice with arrows instead of connections between oxygen and hydrogen atoms. So the way we're going to do is that for every O connected to H, we're going to replace it with an arrow from H to O. I mean H going to O. And then for every place where there is not a connection, we put an arrow going from O to H. And then we're going to get what is called the 6-vertex model, which is basically you have a square lattice, and then we put arrows on every edges of this lattice so that every vertex has 2 incoming arrows and 2 outgoing arrows. So for example, here is an example. If you look at every vertices, they all have 2 in arrows and 2 out arrows. So there are 6 equals to 4 choose 2 possible admissible vertices, which are given here. And so we can view this 6-vertex model as lattice path by doing a bijection between the admissible vertices and these 6 configurations. So basically, whenever there is an up arrow or a left arrow, we think of as there is a path. And when there is a right arrow or a down arrow, then it means that there is no path. Then this allows us to redraw these lattice models as a lattice path on the square grid. So this is going to be useful useful later, but I just want to like put it up here for now.
I noticed in the last slide, it looked like 2 of the paths were the same, the 3rd and the 6th.
Oh, indeed. Wait. I see. So the 3rd one is supposed to be, so whenever there is a up arrow, there is a path. So this guy should be this one. Oh, I made a lot of mistake here. And this guy is correct. This guy is this, correct. This guy is this, this. Oh, this guy should be this. Wait. Oh, this is not even a correct vertex. So, wait, what? Oh, I see. So this one is this where you have path everywhere. Okay, that makes sense now. Because like every arrow in this vertex is up and left. And the bijection is that whenever there is a left or up arrow, then we think of it as there is a path. So in this vertex, there is a path like taking over the entire place. Okay, does that answer your question?
Yeah, thanks.
All right, so, okay. All right, so, okay. So we're going to define a function on these vertices called the Boltzmann weight. And we're going to use this weight function to define a partition function. So notice that the word partition here doesn't mean integer partition. So okay, so here for every vertex, we define its weights as follows. So for the first 2 vertices, they are weighted 1, and the 3rd vertex is weighted 0. Which basically means that we are not allowing to use this vertex, because whenever it's just like not allowed, so we put a 0 over there. And then the last 2 vertices are weighted with some non-trivial thing, which is x sub 1, x sub I, and I means that this vertex appears in the ith row. Okay, so notice that basically we put a non-trivial weight xi whenever there is a up arrow going from the left, coming from the right. So here's a left arrow, here's a left arrow. So really these weights are counting how many left arrows are there in a row of a lattice, and I'll explain it later. And yeah, so this is actually a 5 vertex model because we're not allowing to use one of the configurations. Okay. So given a boundary condition, so we fix the boundary arrows of a lattice, then we can define the partition function to be basically the sum of all possible states, all possible configurations of arrows on this lattice, and the sum over all the products of weights of the lattices. And so here's an example. We fix a boundary like this. And then there are 2 possible fillings of arrows in this lattice under this boundary condition. And the weight of these 2 states are given. And the partition function is the sum of the weight of these 2 states. All right. So now I'm going to define a boundary condition associated to a integer partition lambda. All right, so now we have a lattice. The left and the right boundaries are all arrows going to the right. And now we're going to look at the interior of this partition. In general, it could be a skew partition so that you have some interesting things going on there. But basically, every vertical edge, we put an up arrow, and every horizontal edge, we put a down arrow. So that's going to be the top boundary for our lattice. And then we look at the other boundary of our partition of the Young diagram. Again, we put a down arrow for a horizontal edge and a up arrow for a vertical edge. And then we sort of just stretch it out to a line and then put these arrows onto the bottom boundary of the lattice. So under this boundary condition, the partition function actually equals to the Schur polynomial. And the number of rows is going to be the number of variables in the polynomial. And it's also going to be equal to the maximal entry that you can put on the tableau. All right. So actually, by the way, this lattice model is like well known and probably known like even 20, 30 years ago. But I couldn't figure out where is it first written down? Because that's why I didn't put an explicit citation. But later I'll explain that this is essentially just the non-intersecting lattice path. All right, so now I'm going to talk about the ribbon tableaus and LLT polynomials. So a ribbon is a skew-Young diagram which doesn't contain any 2x2 boxes, 2x2 square. So here are some examples of ribbons. So basically, it has to be a skew-Young diagram, and it doesn't contain any 2x2 block. And so we define another statistic on the ribbon, which is called the spin, which is basically the height of the ribbon minus 1. So for example, the first one, it contains 3 single boxes, so it has height 3, and 3 minus 1 equals to 2. And if you look at the fourth ribbon on the picture, it is just 1 single row, so the height is 1 and the spin is 0. All right, so we're going to define a n-horizontal ribbon strip, which is going to be a tiling of a skew-Young diagram by n ribbons, such that the top right corner of each ribbon is going to like touch the air. So meaning that the top right corner of every ribbon has nothing above it. So for example, in the two examples on the left-hand side, the top right corner of the ribbons are marked, and you can see there's nothing above them. But the other example on the right-hand side is not a horizontal strip, because the top right corner of the bottom ribbon is covered by something above it, so that's not allowed. All right, now with these definitions, we can define what is called the semi-standard ribbon tableau. It's going to be defined in analogous to Young tableaus, but instead of putting boxes on a Young diagram, we put ribbons on a Young diagram. So we first fill out a Young diagram with ribbons, and then fill out the ribbons with numbers. Again, weakly increasing along the rows and strictly increasing along the columns. And there's one restriction, which is that if you look at the sub shape restricting to any number, it must be a horizontal strip. So if you look at the sub-Young diagram, which only contains 1, then it's a horizontal strip. And if you look at the subshape contained restricted to 3, for example, like this guy, it must be a horizontal strip. So in other words, we can think of a ribbon tableau as a sequence of partitions such that, so lambda 1, lambda 0 contained in lambda 1, contained in all the way up to lambda k, such that the difference, the skew shape of a lambda 1 minus lambda 0, lambda 2 minus lambda 1, these skew shapes are all going to be horizontal strips. Okay. Okay. So now we can define the LLT polynomials, which is almost the same way as we define the Schur polynomials, but we have to put another term in there, which is the q to the power of spin of the tableau. So the spin of a ribbon tableau is just the sum of spins of all ribbons in this tableau. And here is an example. So we take the partition 333 and with maximal entry 2. So these 8 tableaux are all possible semi-standard ribbon tableaux in this case. I know the weight of these things are given here. And then so we can sum up out of these terms and we get the LLT polynomial associated to this partition. So first of all, LLT polynomials are symmetric. And if you look at this polynomial, if you switch x1 and x2, you get back to the same thing. And another sort of non-obvious but very interesting fact is that if we set q equals to 1, the LLT polynomial is a product of n Schur polynomials. So in this case, if you set q equals to 1, we get x1 plus x2 to the power of 3. And that's just the Schur function of a single box to the power of 3. All right, so now I've finished all the definitions and I'm gonna sort of prove our first theorem where the lattice model for Schur polynomials indeed gives Schur polynomials. All right, so first of all, we're gonna view a semi-standard Young tableau as a flag of partitions. So we first look at the subshape containing 1, and then the subshape containing 1s and 2s. 1s and 2s and 3s, including 4, and then 5. And then there is a empty partition on the left-hand side that I didn't draw. So for these flags of partitions, we're gonna put a dot or a particle on the vertical edges and the hole on the horizontal edges. And then we're gonna align these particles and the holes in this way. And now by connecting these particles, we get the non-intersecting lattice path associated to this semi-standard Young tableau. And so I claim that our lattice model is nothing but the same lattice path. All right, so here's what we do. So you take the boundary conditions, and then in each of the intermediate rows, we put up and down arrows, just like what we did for the top and bottom boundary. So whenever there is a vertical edge, we put an up arrow, and the horizontal edge, we put a down arrow. So we filled out every rows in this lattice. And then once we've done that, there exists a unique way to fill out the rest of this lattice. And this gives a weight preserving bijection between the set of semi-standard Young tableaux and the set of admissible states in the lattice model under this boundary condition. So here is why this lattice is just the same as the lattice path, because if you follow the up and left arrows and just highlight them, and you realize that the movement of the arrows is just the movement of the lattice path. And again, as I mentioned before, the Boltzmann weight that we define is really just counting the number of left arrows and the number of left arrows in each row is exactly the number of the boxes with that number, because between every row, you just remove those boxes. Okay. Are there any questions so far? All right, so now let's look at the Boltzmann weights again. So the zero weighted term, that vertex is when the path could intersect, right? So we want to find non-intersecting lattice path. And that's why we give it a weight 0 so that it will never show up. And that guarantees that we never have an intersection. And again, every left arrow gets a weight of xi. So if you look at this lattice, model again, in the first row, we have 3 left arrows, and that corresponds to that there are 3 boxes of 1s. And in the second row, there are 3 left arrows of 2s, and it corresponds to that there are 3 2s in the tableau. So I won't give a rigorous proof, but I hope that the proof by example is good enough to convince you guys that this is indeed a weighted preserving bijection.
So when you are saying the third one, that is the path intersection, but how come the first one, the fourth one, they are not considered intersecting paths?
Because we look at the left arrows and up arrows as path. Right, so this guy is just you go left and up. This guy is you go left and down. And for the fourth vertex, there's no path at all. And this guy you go up and left. This guy you go up. And if you just play around with these 5 configurations, there is no way that you can get a intersection. The only possible place when you can intersect is when you use the third vertex, which is like you have a path taking over every edge, and that's exactly when the intersection happens.
I see. Thank you.
All right. Okay, so now let's try to generalize this to ribbon tableaus, which is.
And there's one more question from Stephen or Stefan. The last one is go left and left, not left and down. Yeah.
Thank you. Yes, it is indeed going from left to left. Thanks. Okay. All right. So how are we going to do this for ribbon tableau? I mean, it's pretty mysterious when we first look at it, and we try to do the same thing, right? So we take a ribbon tableau as a sequence of partitions. And then we draw a bunch of particles and holes. Now it's red and black. It's red and black circles. So we associate a sequence of red and black dots to each partition in the same way, and then we put them on a lattice like this. And the goal is to connect these red dots in a reasonable way. So it turns out that the correct thing to do is that you allow to go up or left by a multiple of 3. This is a 3 ribbon tableau, so we allow them to move to the left in steps of multiples of 3. In general, if it's an n ribbon tableau, then they can move to the left in multiples of n. So the problem is that this path is intersecting. So it's not, which basically means that there's no way to give a 6 vertex model for these paths. And in fact, we're going to see these as colored non-intersecting lattice path. So in this case, we colored them in 3 colors, red, blue, and green. So each row, each column is going to correspond to a color, right? And then when you connect these red dots, you're going to never leave this color. So we are going to get a bunch of lattice paths that are colored in these 3 different colors. And it turns out that we want to, like the only thing that we want to put is that you cannot intersect with a path that is the same color. So red cannot intersect with red, but the red can intersect with blue.
So what I think what is actually happening here, that if you're familiar with the quotient of a partition, that the separation of these colors is actually that you have a partition given by the quotient of the a partition for each part in this quotient. And this is what you already said, that the product, that the LLT polynomial, when you plug in 1, is the product of the Schur polynomial. So this must be actually all these colors, I think.
Exactly.
Okay.
So I will actually talk about this in just a couple of slides. So yes,
Okay.
you can separate these lattice paths into different colors, and then you get, like in this case, 3 Schur polynomials, 3 9-intersecting lattice paths, which gives us Schur polynomials.
And what you kind of have here is this abacus model by James and Kerber, if you're familiar with this.
I am not familiar with that.
Okay. That's something that you could check out.
Yeah, thanks. Yeah. Okay. So another cool thing is that we can recreate this path on the ribbon diagram, on the Tableau diagram. And the rule is that in each ribbon, we're going to let the top right particle to move all the way to the bottom left. And then the other particles in this ribbon is going to move up. So using this rule, we get the path picture on the ribbon tableau that is given here. And as you can see, these paths are exactly the same as the lattice path picture. And moreover, the spin in the ribbon tableau is just the number of intersections in this lattice path, which is not, I guess, not very obvious, but once you stare at it for a moment, you believe that it is true. Okay, then how are we going to make a lattice model? All right, so this is going to be our vertices, which has one vertical strand and 3 horizontal strands, which are intertwining. And here is what a one row lattice looks like. And then the entire lattice model looks like this. So again, we put a boundary condition basically in the same way as we did for the Schur polynomial. We take a partition and we look at the interior and the outer boundary. And then we put up arrows and down arrows according to the vertical and horizontal edges. All right, so we're going to define some weight on these, what we call the ribbon vertices. So first of all, we're going to call there are 2 types of edges, the twisted edge and the straight edge. So first of all, again, the number of in arrows is going to be the same as the number of outgoing arrow. And secondly, we do not allow change of arrow on straight edges. For example, This vertex right here is not allowed because you switched from left arrow to right arrow along this straight edge. And then we're going to define a Boltzmann weight on these these ribbon vertices. So what I've put here right now is the Boltzmann weight for our 6 vertex model or 5 vertex model. And so these weights are indeed just the weights for the ribbon vertices are in just Q analogs of the weight for the 6 vertex model. All right, so these are the same configurations on the twisted edge and the vertical edge. And then I'm going to throw in some Qs. So we basically multiplied everything except for the 4th one by Q to the power of S. And S means the number of left arrows in the area, in the edges circled by the blue circle. Right. So in a similar spirit, there is a weight preserving bijection between the admissible states of this lattice and the set of semi-standard ribbon tableaus of the partition for the boundary condition. So again, we fill out the intermediate rows according to the sequence of partitions. And then in a similar way, there exists a unique way to fill out the rest of the edges of this lattice. So I'm gonna omit every right arrow. So whenever there is not an arrow, it's gonna be a right arrow. So I'm only drawing the left arrows here. All right, so this is how we're gonna fill out the bottom row, and then the next row, and then the next 2 rows. All right. So again, I'm gonna prove by this example that this is actually a weighted preserving bijection. So let's see how this looks like the path.
I have a question.
Yep.
So in the 1, 2, 3, 4, the 5th column, at the very top, you have the arrows going from the bottom right to the top left. But maybe I missed it verbally, but I thought the arrows can only be placed when they're going from the bottom left to the top right, or vice versa.
You mean?
Yeah. Like 1st row, 5th column.
Oh, I see. Oops. Okay, right
Yeah,
here.
so like there, those arrows, so are you just saying like this is just the flow from the previous one, or because I thought those arrows could only exist if they're from the bottom left to the top right, or I guess I'm confused as to what's happening here.
I see. So let me go back to the weights here. I think I understand why you're confused. So where are the weights? Okay.
Yeah.
So the thing that we are not allowing is this configuration cannot happen on the twisted edge.
No, so like, okay, so here, if you look at the 6 we have here, all the arrows are from the bottom left and the top right, but the other 2 lines never have a arrow thing. So
the other
like,
2 lines. Oh, I see. So the
yeah.
other 2 lines can have any arrow, any if
Okay,
it's
so it's
left or right,
arbitrary arrows.
arbitrarily, as long as you do not change along those 2 edges. So the only constraint that we put on the straight edges is that you cannot change arrow, but they can be any arrow, that anything you want.
Okay, so I missed R2. That works. Thank you. Sorry.
Cool. So.
But the 2 parallel straight edges, can they have different directions?
They can.
Okay.
They can have 2 different directions. Okay, so yeah, here we go. So here is a combination of the lattice model, the colored lattice path picture, and the ribbon tableaus picture. And now I'm gonna highlight something on the lattice model, which, as you can see, is exactly matching up the colored lattice path that we are drawing on the bottom right. Okay, so by introducing these intertwining edges, some like magic happened that, you know, you can, these arrows, because they cannot change on the straight edges, they have to move all the way to the left in steps of multiples of 3. And then, you know, and then everything else basically follows the same spirit of the 6 vertex model for the Schur function. So it's pretty clear that the x weight, or I mean, at least it's sort of not very difficult to see that the x weights are matching up, but it's a little like tricky to see why the q's are correct. So, okay, so here's another mistake I make. I'll explain it later. So in these black dots, it basically means that in this case, you get a power of q because there's a straight edge of left arrows that is intersecting with some other arrows. Okay, what's wrong is right here. So this guy is not q squared, but there's another q right here. So this is just a q, and there's another q here. So whenever you have a straight edge of left arrows happen in the same place of some other up arrows or left arrows, then you will get a q, get a power of q. And that's exactly when the paths intersecting. Which means that, you know, this is a weight preserving bijection. So for example, in this vertex right here, there is a path moving along this blue edge, this blue path, and there's this red path going through it, and this exactly capturing the intersection at this place, where you have a blue and the red intersected, and the second Q in this row is capturing the intersection that is happening right here. And the third Q is this intersection, and the fourth Q is this intersection. So we define our weights in a way that whenever there is intersection of path, we put a Q in there.
So how in the bottom left you have the two additional intersections? Is it because you can kind of undo that intersection that in the two on the right that you don't have that intersection showing up?
Oh, what do you mean, like undo the intersection?
Because you do the same intersection twice, right? The red and green, and then the red and green again on the same lines. So it's kind of like you can flip them, and it doesn't really change much. I'm thinking like a braid relation is the image I have in my brain, but this is not a braid relation, obviously. Or like knot theory, you just kind of pull the strings, because like you don't have the same intersections on the two on the right, the bottom right and the top one. That those intersections don't appear. So is that how I should be thinking about this?
Yeah, actually, what we should be thinking is that the number of row actually tells us where the intersection happens. I didn't say that explicitly because I don't want to introduce unnecessary complication. But so for example, this one is the 1, 2, 3, 4, 5, 6 is the 7th row. So which means that we should look at this 1, 2, 3, 4, 5, 6, 7. And it's going to be this intersection. And this row is the 6th row. So it's going to be this 1, 2, 3, 4, 5, 6. You go right here. And this is the intersection that's happening in the 6th row. I mean, column, sorry. I've been, not row, I mean. Does that make sense?
I think so.
Okay. Oops. All right, so I'm almost done here, I believe. So let me move on to some other stuff. Okay, so here's a more concrete example of what happened for just one single ribbon. So you put the arrows like this, and then you complete the lattice and you get the path. And then for every ribbon, we pick up one weight of x from the vertex, the leftmost vertex. And in this case, we get 2 powers of q's, which is exactly captured by these 2 vertices. And so you can sort of generalize this by gluing up a bunch of single ribbons to get a horizontal strip. And every horizontal strip going to be corresponds to a single row lattice. So that's basically how the proof actually works. Okay, and therefore the partition function of this lattice equals to the LLT polynomials. And so here is the thing that we were discussing before, that why LLT polynomials are Q analogs of Schur polynomials. So you take this colored lattice path, and then you separate the colors. So you're going to get the lattice, a non-intersecting lattice path with the red path and the blue and the green. And so, and these 3 guys are going to be corresponding to young semi-centered young tableaus. So then you get 3 Schur functions, Schur polynomials. So this explains why LLT polynomials, when you evaluate at q equals to 1, you get products of Schur polynomials. How did you place the blue lines on the right side of the equation? Oh, okay, so
Maybe Sylvester, is it just because that's like you're looking at, like you're restricting to the colored or something like that? So
yeah,
like
we're restricting to these 4 columns. These 4 columns. So that gives us, oops, this.
I see. So
and if we restrict to the red columns, so the columns are indexed by these colors. So the red column is this.
thank you.
Is this map different from the Shannon-White bijection between ribbon tableaus and tuples of semi-centered tableaus? I'm actually not aware of that map, but I think this is pretty much the same as Hyman's definition, or I mean the like tuple definition by Hyman and some other guy whose name I don't remember. But I'm pretty sure this is known in the literature like a long time before us. I mean, I should like understand better about it. Okay.
On the diagram on the left, can you switch the color of the green one with the red one that is on the right of the green one?
Sorry, what do you mean?
Like on the one on the left, right now you have a green path sort of sandwiched between two red paths.
Yeah.
So I'm wondering, can you switch the color of the green path and the red path that is on the right of the green path? So when you switch those two colors, you don't violate the rule that two colors, you don't violate the rule that two paths of the same color intersect.
Right. I mean you can because well, because in the case of q equals to 1, we don't care about the intersections between different colors, and that's why you can separate them. And then after you separate them, so it's it's not an ordered triple, which means that I'm not sure if I understand your question correctly, but I believe the answer is yes.
Okay, thank you.
Okay. All right. All right, so the last thing that I want to talk about is Yang-Baxter equation. So for the 6-vertex model, we're going to introduce some new types of vertices, which we're going to denote R1 vertices, which looks like axis. And then so the Yang-Baxter equation means that, so it's a system of equation defined by sort of some mini lattices, looks like this, the star triangle inequality. So for any fixed boundary, alpha, beta, gamma, A, B, and C, you're able to choose any arrow of these 3 interior edges. And we want to set a weight for these R vertices such that the partition function of these 2 mini lattices are always going to be the same. So whenever there is a solution to the Yang-Baxter equation, it means that the partition function is symmetric. So here's why. So we're going to look at the lattice, and then we're going to add a y vertex, an R vertex to it. And now notice that the row indices are changed by introducing this x vertex. And then using the Yang-Baxter equation, we can just like pop this vertex in, and then again, and then all the way to the right. So what happened is that the partition function doesn't change because of the Yang-Baxter equation, but the first 2 rows are swapped. So x1s becomes x2 and x2s becomes x1. And because, and then we just take off that extra vertex, and they have the same weight, so we can cancel them out. And then which means that the partition function of these 2 lattices with the first 2 row indices changed are the same. They have the same partition function. And you can do this for any adjacent rows. And because the symmetric group is generated by involution, adjacent transpositions, it does tell us that the partition function or the symmetric polynomial is invariant under symmetric group action. And so here is the solution to the YBE, the Yang-Baxter equation of the 6-vertex model case. And so what happens when we look at the Yang-Baxter equation for a ribbon vertex, and we're going to call these new vertices the Rn vertices, which is basically n different R vertices stacking up on each other. And then it's the same thing. We want to solve for a weight for these vertices. So it looks like it's, well, because you have, in general, you have many interior edges that you need to fill in. So it looks like it's a very large system of equations. But in fact, it is not, because most of the interior edges are fixed by the boundary condition, because remember, we have the rule that arrows cannot change along straight edges. So really, on the left-hand side, we have 3 variables, and on the right-hand side, we have 3 variables. So we can solve the Yang-Baxter equation just the same way as we solve for the Schur polynomial case, but just with some extra attention to the Q's, and it's basically like you can solve it by hand using some case-by-case analysis. So I'm not going to write down the exact solution to this Yang-Baxter equation, but in short, these Rn weights are Q analogs of products of these R1 weights, which is not surprising because LLT polynomials are Q analogs of products of Schur polynomials. Okay. All right, so that's the end of my talk. Thanks for listening.
So thank you, Sylvester. That was awesome. And you've sparked a lot of discussion in the comments as well. So let's give Sylvester a first round of applause.
Usually,
Yeah.
you know,
Very
we
nice.
usually have,
Great. Are there questions from the audience?
So I don't know anything about LLT polynomials, so this might be an ill-informed question. You have, it's essentially, it's a graded symmetric function, right? I mean, graded by the power of Q, right? It's, you know, you could think of it as polynomial in Q with coefficients in, you know, symmetric polynomials, right? Is there, I guess, a satisfying graded representation that polynomial is the representation, you know, graded you know, under the Frobenius characteristic of, or I guess equivalently, do we know anything more about what those coefficients are in terms of like any of the standard symmetric function bases?
I see. So I'm wondering. Okay, so there is a conjecture that the, I mean, not really a conjecture, but a theorem that the LLT polynomials are positive in the Schur basis. So you're able
So
to
that the
write
coefficients are also Schur positive.
Yes, the coefficients are powers of Q, and it is not known what would be a combinatorial formula for those coefficients, I guess, but I believe it is proved by Hyman and another name I forgot, using some representation theory.
Cool. Thank you.
Other questions from the audience? I'll check the chat, see if there are questions in the chat. I don't see any. So, okay, seeing none, I'll say we can turn off, we'll thank Sylvester again, then we'll turn off the recording and leave a little bit of time for unrecorded questions.